Hey everyone, welcome back to the channel. Engineer Empire here. I'm a software engineer turned corporate VP and head of technology. I dive into topics like engineering, finance, and business. If that interests you, please hit like or subscribe. Today I'm reacting to When Abandoned Mines Collapse.
In December of 2024, a huge sinkhole opened up on I-80 near Wharton, New Jersey, creating massive traffic delays as crews worked to figure out what happened and get it fixed. Since then, it happened again in February 2025 and then again in March. Each time, the highway had to be shut down, creating a nightmare
That's actually fairly frequent.
for commuters who had to find alternate routes. And it's a nightmare for the DOT too, trying to make sure this highway is safe to drive on, despite it literally collapsing into the earth. From what we know so far, this is not a natural phenomenon, but one that's human-made. It looks like these issues were set in motion more than a century ago when the area had numerous underground iron mines. This is a really complex issue that causes problems around the world, and I built a little model mine in my garage to show you why it's such a big deal. I'm Grady, and this is Practical Engineering. We've been extracting material and minerals from the earth since way before anyone was writing things down. It's probably safe to say that things started at the surface. You notice something shiny or differently colored on the side of a hill or cliff, and you take it out. Over time, we built up knowledge about what materials were valuable, where they existed, and how to efficiently extract them from the earth. But of course, there's only so much earth at the surface. Eventually, you have to start digging. Maybe you follow a vein of gold, silver, copper, coal, or sulfur down below the surface, and things started to get more complicated because now you're in a hole. And holes are kind of dangerous. They're dark, they fill with water, they can collapse, and they collect dangerous gases, so in many cases, even today, it makes sense to remove the overburden, the soil and rock above the mineral or material you're after. Mining on the surface has a lot of advantages when it comes to cost and safety, but there are situations where surface mining isn't practical. Removing overburden is expensive, and it gets more expensive the deeper you go. It also has environmental impacts like habitat destruction and pollution of air and water. So, as technology, safety, and our understanding of soil and rock mechanics grew, so did our ability to go straight to the source and extract minerals underground. One of the major materials that drove the move to underground mining was coal. It's usually found in horizontal formations called seams that formed when vast volumes of Paleozoic plants were buried and then crushed and heated over geologic time. At the start of the Industrial Revolution, coal quickly became a primary source of energy for steam engines, steel refining, and electricity generation. Those coal seams vary in thickness, and they vary in depth below the surface too, so many early coal mines were underground. In the early days of underground mining, there was not a lot of foresight. Some might argue that's still true, but it was a lot more so a couple hundred years ago. Coal mining companies weren't creating detailed maps of their mines, and even if they did, there was no central archive to send them to. And they just weren't that concerned about the long-term stability of the mines once the resources had been extracted. All that mattered was getting the coal out of the ground. Mining companies came and went, dissolved or were acquired, and over time, a lot of information about where mines existed.
An interesting problem that he's describing. So, effectively, what he's saying is that after companies or these individuals who were mining could mine into various directions, and then they would potentially not even track exactly where everything was laid out in either at all or in necessarily enough detail to be useful later on down the road. And also, these things just might never have been passed along. Maybe if you're a company who's mining and you've shut down that mine, who is going to know the map of the inside of that mine other than you? Probably no one. And so this is an interesting aspect that I also have not thought of. This is one of my favorite parts about this channel, is learning more about the physical world that we live in, especially being a software engineer by trade. This is something I don't think about as much. And so this is where, like, if you have some server or some software somewhere that nobody knows what it does. Like, you can always just shut it down and no harm, no foul for the most part, unless you actually need it to keep functioning. But you don't have these catastrophic issues like if you had worked on a mine and you left it and abandoned it, and then nobody knows what's going on there, that it could lead to some serious issues down the road.
And their condition was just lost. And even though many mines were in rural areas far away from major population centers, some weren't, and some of those rural areas became major population centers without any knowledge about what had happened underneath them decades ago. An issue that confounds the problem of mine subsidence is that in a lot of places, property ownership is split into two pieces, surface rights and mineral rights, and those rights can be owned by different people. So if you're a homeowner, you may own the surface rights to your land while a company owns the right to drill or mine under your property. That doesn't give them the right to damage your property, but it does make things more complicated since you don't always have a say in what's happening beneath the surface. There are myriad ways to build and operate underground mines, but especially for soft rock mining like coal, the predominant method for decades was called room and pillar. This is exactly what it sounds like. You excavate the ore, bringing material to the surface, but you leave columns to support the roof. The size, shape, and spacing of columns are dictated by the strength of the material. This is really important because a mine like this has major fixed costs: exploration, planning, access, ventilation, and haulage. It's important to extract as much as possible, and every column you leave supporting the roof is valuable material you can't recover. So there's often not a lot of margin in these pillars. They're as small as the company thought they could get away with before they were finished mining.
That's another interesting problem, which is for security of the mine itself, you're literally eating into your own profit margin. That is definitely a tricky place to be, I would assume, for engineers on that front. I know risk on my end of the spectrum has much less catastrophic or deadly implications. More so, the worst things that are going to happen are like some personal information gets leaked, which isn't great, and people, I'm sure, wouldn't want that to happen. I've never actually allowed that to happen in the past. But certainly that's a whole other scale in my mind than you actually potentially having a cave-in and your employees are trapped in the mine, or whatever is above the mine collapses and potentially puts many people's lives in danger. And so actually having to have risk as a very concrete, potentially life or death scenario is an interesting trade-off to have to actually manage and traverse as an engineer of a different discipline.
Built a little room and pillar mine in my garage. I'll be the first to admit that this little model is not a rigorous reproduction of an actual geologic formation. My coal seam is just made of cardboard, and the bright colors are just for fun. But I'm hoping this can help illustrate the challenges associated with this type of mine. I've got a little rainfall simulator set up because water plays a big role in these processes. This first rainfall isn't necessarily representative of real life since it's really just compacting the loose sand, but it does give a nice image of how subsidence works in general. You can see the surface of the ground sinking as the sand compacts into place. But you can also see that as the water reaches the mine, things start to deform. In a real mine, this is true too. Stresses in the surrounding soil and rock redistribute over time from long-term movements, relaxation of stresses that were already built up in the materials before extraction, and from water. I ran this model for an entire day, turning the rainfall on and off to simulate a somewhat natural progression of time in the subsurface. By the end of the day, the mine hadn't collapsed, but it was looking a great deal less stable than when it started. And that's one big thing you can learn from this model. In a lot of cases, these issues aren't linearly progressive. They can happen.
I really enjoy these mock-ups and these models that he builds. They're really great for demonstrating the examples that he has, and it's cool to be able to see them and interact with them.
And in fits and starts, like this small leak in the roof of the mine. You get a little bit of erosion of soil, but eventually enough sand built up that it kind of healed itself. And for a while, you can't see any evidence of it at the surface. The geology essentially absorbed the sinkhole by redistributing materials and stresses, so there's no obvious sign at the surface that anything wayward is happening below. In the US, there were very few regulations on mining until the late 19th century, and even those focused primarily on safety of the workers. There just wasn't that much concern about long-term stability, so as soon as material was extracted, mines were abandoned. The already iffy columns were just left alone, and no one wasted resources on additional supports or shoring. They just walked away. One thing that happens when mines are abandoned is that they flood. Without the need to work inside, the companies stop pumping out the water. I can simulate this on my model by just plugging up the drain. In a real soft rock mine, there can be minerals like gypsum and limestone that are soluble in water. Repeated cycles of drying and wetting can slowly dissolve them away. Water can also soften certain materials and soils, reducing their mechanical strength to withstand heavy loads, just like my cardboard model. And then, of course, water simply causes erosion. It can literally carry soil particles with it, again causing voids and redistribution of stresses in the subsurface. This is footage from an old video I did demonstrating how sinkholes can form. The ways that mine subsidence propagates to the surface can vary a lot based on the geology and depth of the mine. For collapses near the surface, you often see well-defined sinkholes where...
Wow, this is a pretty serious sinkhole. I think I've only really seen some of the shots that they had earlier near like the highway where you could see it, but it was probably maybe no more than 6 to 10 feet deep would be my guess. Hard to tell from that angle, but this is obviously a huge one in comparison. Like, it's unclear whether or not you can even see the bottom of this from the current angle and whether we will see it in this shot.
Where the soil directly above the mine simply falls into the void. And this is usually a sudden phenomenon. I flooded and drained my little mine a few times to demonstrate this. Accidentally flooded my little town a few times in the process, but that's okay. You can see in my model, after flooding the mine and draining it down, there was a partial failure in the roof and a pile of sand toward the back caved in. And on the surface, you see just a small sinkhole. In 2024, a huge hole opened right in the center of a sports complex in Alton, Illinois. It was quickly determined that part of an active underground aggregate mine below the park had collapsed, leading to the sinkhole. It's pretty characteristic of these issues. You don't know where they're going to happen, and you don't know how the surface soils are going to react to what's happening underneath. Subsidence can also just look like a generalized and broader sinking and settling over a large area. You can see in my model that most of the surface still looks pretty flat, despite the fact that it started here and is now down here as the mine's supports have softened and deformed. This can also be the case when mines are deeper in the ground. Even if the collapse is sudden, the subsidence is less dramatic because the geology can shift and move to redistribute the stresses. And the subsidence happens more slowly as the overburden settles into a new configuration. In all cases, the subsidence can extend laterally from the mine, so impacted areas aren't always directly above. The deeper the mine, the wider the subsidence can be. I ran my little mine demo for quite a few cycles of wet and dry just to see how bad things would get. And I admit I used a little percussion at the end to speed things along. Let's just say this is a simulation of an earthquake on an abandoned mine. You can see that by the end of it, this thing has basically collapsed. And take a look at the surface now. You have some defined sinkholes for sure, and you also have just generalized subsidence, sloped and wavy areas that were once level. And you can imagine the problems this can cause. Structures can easily be damaged by differential settlement, pipes break, foundations shift and crack. Even water can drain differently than before, causing ponding and even changing the course of rivers and streams for large areas. And even if there are no structures, subsidence can ruin high-value farmland, mess up roads, disrupt habitat, and more. In many cases, the company that caused all the damage is long gone. Essentially, they set a ticking time bomb deep below the ground with no one knowing if or when it would go off. There's no one to hold accountable for it, and there's very little recourse for property owners. Typical property insurance specifically excludes damage from mine subsidence. So in some places where this is a real threat, government-subsidized insurance programs have been put in place. 8 states in the US, those where coal mining was most extensive, have insurance pools set up. In a few of those states,
That is interesting. I actually didn't know that mine subsidence was even an option for insurance and that it's something that explicitly is not covered. Seems to be one of those gotchas that insurance companies actually get, which is like the most likely bad things to happen in your area is always the things they don't want to insure you for. It's always the other things that they would like to insure you on. But it's certainly curious. And he said 8 states. I actually don't know which states those are going to be off the top of my head. That one referenced Pennsylvania, so maybe he'll go through which states this also covers.
it is a requirement in order to own property. The federal government in the US also collects a fee from coal mines that goes into a fund that helps cover reclamation costs of mines abandoned before 1977 when the law went into effect. That Federal Mining Act also required modern mines to use methods to prevent subsidence or control its effects because this isn't just a problem with historic abandoned mines. Some modern underground soft rock mining doesn't use the room and pillar method, but instead a process called longwall mining. Like everything in mining, there are multiple ways to do it. But here's the basic method. Hydraulic jacks support the roof of the mine in a long line. A machine called a shearer travels along the face of the seam with cutting drums. The cut coal falls onto a conveyor and is transported to the surface. The roof supports move forward into the newly created cavity, intentionally allowing the roof behind them to collapse. It's an incredibly efficient form of mining, and you get to take the whole seam rather than leaving pillars.
And it's interesting that they sort of like intentionally collapse small portions so it continues to fill in the space over time. It's one way of solving that problem.
Behind to support the roof, but obviously, in this method, subsidence at the surface is practically inevitable. Minimizing the harm that subsidence creates starts just by predicting its extent and magnitude. And just looking at my model, I think you can guess that this isn't a very easy problem to solve. Engineers use a mix of empirical information, like data from similar past mining operations, geotechnical data, simplified relationships, and in some cases, detailed numerical modeling that accounts for geologic and water movement over time. But you don't just have to predict it, you also have to measure it to see if your predictions were right. So mining companies use instruments like inclinometers and extensometers above underground mines to track how they affect the surface. I have a whole video about that kind of instrumentation if you want to learn more after this. The last part of that is reclamation, to repair or mitigate the damage that's been done, and this can vary so much depending on where the mine is, what's above it, and how much subsidence occurs. It can be as simple as filling and grading land that has subsided all the way to extensive structural retrofits to buildings above a mine before extraction even starts. Sinkholes are often repaired by backfilling with layers of different sized materials, from large at the bottom to small at the top. That creates a filter to keep soil from continuing to erode downward into the void. Larger voids can be filled with grout or even polyurethane foam to stabilize the ground above, reducing the chance for a future collapse. I know coal and mining in general can be a sensitive topic. Most of us don't have a lot of exposure to everything that goes into obtaining the raw resources that make modern life possible. And the things we do see and hear are usually bad things, like negative environmental impacts or subsidence. But I really think the story of subsidence isn't just one of mining is bad, but really, mining used to be bad, and now it's a lot better, but there are still challenges to overcome. I guess that's the story of so many things in engineering, addressing the difficulties we used to just ignore. And this video isn't meant to fearmonger. This is a real issue that causes real damages today, but it's also an issue that a lot of people put a great deal of thought, effort, and ultimately resources into so that we can strike a balance between protection against damage to property and the environment and obtaining the resources that we all depend on.
Thank you for watching. If you've enjoyed what you've seen, please hit like or subscribe. I will see you around.